Hello everyone, welcome to YourPedia Education. So today we are going to discuss some questions from Electronics Device and Circuit EDC. This is very good subject. You can say that it is having around 10% weightage in your BEL or BDL exam. Mostly questions from this subject you can say are theoretical types, right? If you are preparing for BDL or BEL exam, right, it is the most important subject, and these questions are really important for that exam, you can say, right? If you want to prepare for that exam, we already launched one module for that one. You can join that module, right? And you start preparing for this exam, right? Already hundreds of students are already joined that course, and you may join that course to get help in your exam. So let us discuss some more questions from the electronics device and circuit, right? The first question is, n-type silicon is obtained by doping the silicon at 300 Kelvin. If you are doping the silicon at 300 Kelvin and you want that silicon is become n-type silicon, so which impurity atom you should, or which doping atom you should introduce in that one, right? See, remember one thing, whenever you are making a p-type semiconductor, p means what? Negative type semiconductor. In negative type semiconductor there are charge carrier which are electrons. So electron will be given to your silicon by a pentavalent atom, because silicon has 4 electron in outermost cell. If you introduce a pentavalent atom, pentavalent means its outermost cell contain 5 electrons. So if you introduce a pentavalent atom inside that one, it means it will give one extra electron to your structure. So that's why if you introduce the pentavalent impurity inside the semiconductor, then it is become n-type. And if you introduce the you can say trivalent impurity inside the silicon, then it is become p-type semiconductor. If we are making the n-type semiconductor, the pentavalent impurity means fifth group elements. So generally what we are using, in the fifth group we have phosphorus, arsenic and antimony. These are the materials which can be used as a pentavalent impurity. So from the option, germanium is germanium having 4 electron in outermost cell, it is a semiconductor, it cannot be used as a impurity atom. Aluminium is a third group element. Boron is also third group element. Third group element make the semiconductor as a p type, not n type. Then only phosphorus will make the semiconductor as a p type. So remember the third group and fifth group. Third group make the semiconductor. If you introduce the impurity from the third group, that will make the semiconductor. If you introduce the impurity from the third group, right, third group, then it will make the semiconductor as a p type. And if you introduce the impurity from the fifth group, right, see here, this is your not fifth, sixth, this is your fifth group, fourth group and third group, right? Generally the fourth group elements are the semiconductor. Germanium, silicon, carbon, germanium, silicon are the fourth group element. They are the semiconductor. Carbon is not the semiconductor, right? Because carbon have different properties, like sometime it is a pure insulator, sometime it is a pure conductor, like graphite is a conductor. So carbon has a different property. Carbon does not follow the semiconductor property. That's why carbon is not working as a semiconductor. We generally take from the fourth group, we generally take that silicon and germanium as a semiconductor. Some compound semiconductors are also there. They are not that much part of this course right now, right? Now the third group element are generally aluminium, boron, aluminium. These are the third group element. Third group element have 3 electrons in its outermost cell, right? So that's why they are called as trivalent impurity. Trivalent impurity, when you introduce, that will be make the semiconductor as p type. When we introduce, when we go for the fifth group generally have phosphorus, arsenic and antimony. So this fifth group, when we introduce the fifth group impurity, when we introduce phosphorus, arsenic or antimony as a dopant inside the semiconductor, right, then it will make the semiconductor as a p-type semiconductor. This is the main thing you should know about the impurity atoms, right? So it means what will be the answer? The answer is phosphorus. Move to the next question. Doping of boron in silicon. Doping of boron in the silicon results. See, this is the similar type of question. The way of asking this question is different from the previous one. He is asking that doping of boron in silicon results in. If you introduce the doping of boron, boron is third group element. If you introduce the third group element inside, if you introduce the third group element, right, doping of third group element in the silicon or germanium semiconductor, then it will make that semiconductor as a p-type semiconductor. I already discussed this thing in detail in the previous question, right? So you can read this thing. I already discussed everything with you, right? Next, state the correct statement regarding the semiconductor devices. Okay, which statement? Which statement is correct regarding the semiconductor device? Electrons and holes are of equal density in an intrinsic semiconductor at equilibrium. See, whenever we are talking about an intrinsic semiconductor, the number of electrons and number of holes are always same. Remember that thing, right? The first is the answer, right? There are maybe several statements are correct, right? He is asking for the correct statements, right? The first statement is correct because whenever we are talking about an intrinsic semiconductor, in intrinsic semiconductor, the Ni is called as intrinsic carrier concentration. So whenever you have an intrinsic semiconductor, there are electrons and holes are equal. Remember one thing. What is happening how you make an intrinsic semiconductor? There is no impurity. So in a semiconductor, if you increase the temperature, the covalent bond will break. When one covalent bond is break, then one electron is free and that electron left behind one hole. So whenever one covalent bond is break, that will generate one electron and one hole. Remember that thing. So inside the pure semiconductor, whenever you increase the temperature, or inside the intrinsic semiconductor, whenever you increase the temperature, whenever the covalent bonds are break. So if one covalent bond break, one electron hole pair is generated. If 1000 covalent bonds generate, 1000 electron and holes are generated there. So what you are seeing, see, inside the pure semiconductor, if we increase the temperature, the electron covalent bonds are break and electron hole pair are generated, but the number of electron and holes are remain equal, because there are if one covalent bond is break, then one electron and one hole pair is generated, right? So that is the thing basically inside the semiconductor, inside the pure or intrinsic semiconductor, number of electrons and number of holes are equal, and they are equals to Ni, intrinsic carrier concentration. Collector region is generally more heavily doped than base region in the BZT. See, if you talk about the BZT, right? If you talk about the BZT, inside the BZT there are three regions. One is collector, one is base, another one is emitter. Emitter is heavily doped, collector is moderately doped, and base is lightly doped. I already discussed this thing in class in detail, right? Why we are taking this thing. Base width, if I am talking about the base width, right? Oh sorry, width of the each region, base is smaller, emitter is moderate width, and the collector has the wider width. Or you can say collector has the wider area, emitter has moderate area, base has smaller area. So that is the main reason here. So this option is not correct. Heavily doped is what? Heavily doped is emitter. The total current is spatial constant in the two terminal electronics devices in dark under steady state condition. That is correct. So if you go to photoelectronics devices, that is correct. Mobility of electron always increase with increasing the temperature in silicon beyond 300 Kelvin. See, whenever you increase the temperature further, the mobility will decrease. The mobility is the inverse function of the temperature. So this is not correct. So only two statements are correct, A and C. Right, next. Out of the following material, which one having the maximum forbidden band gap? See, if I am talking about the band gaps, if I'm talking about the band gaps inside the, if I'm talking about the metal, this is the metal. Inside the metal, the valence band will be overlapped with the conduction band. So there is no forbidden energy gap inside the metals. So aluminum is the metal, so there is no forbidden energy band gap inside this, so it is not having answer, right? Next one is semiconductor. Semiconductor have the band gap that is around 1.1, 1.2, 1.3, or you can say from 1 to 2 electron volts, and inside the insulator this band gap is very high, around 6 electron volts or greater than. So basically there are three types of material. First one is metals, right, or you can say the conductor. Second one is semiconductor, and third one is insulator. So insulator has the wider band gap. So inside this one, aluminum is a conductor, silicon is a semiconductor, germanium is a semiconductor, SiO2, silicon dioxide. This is the important property, that SiO2, this is silicon dioxide, it is an insulator. So what will be the answer? D. So that is the main reason why we are using the silicon. See, you see that most of the devices inside your you can say in electronics, we are generally making all the devices from the silicon, right? If you see the MOSFET or everything, if you have a IC, and inside the IC, if you want to provide the insulation between two devices, so that insulation will be provided by what? That will be provided by insulator. So it is easy to make insulating material by using silicon, because when you oxidize the silicon, then it will make a silica. Silica is what? SiO2, silicon dioxide, that is work like a insulator. So remember, SiO2 is an insulator. That is the most important property of the silicon. That's why main reason. This is one of the reason. Another reason that silica is easily available. Silicon is easily available inside your environment, right? So what is the answer for this question? The forbidden energy gap is the maximum inside the insulator, and silicon dioxide is a insulator here, or silica is the insulator here. The probability that an electron in a metal occupy the Fermi level. See, always remember at Fermi level, either it is a metal or either it is a semiconductor. The Fermi level is the energy level where the probability of finding one electron is 1 by 2, 50% you can say. So the Fermi level is always the energy level where the probability of occupying by an electron is 50%, or 0.5 or 1 by 2. So answer is C. Drift current in a semiconductor depends upon. See, whenever we are talking about the drift current, there are two types of current inside the semiconductor. One is drift current, another one is diffusion current. Drift current is due to applied electric field, right? Diffusion current is due to concentration gradient. So it is only the electric field, only carrier concentration, both electric field and carrier concentration, right? See, basically if I'm talking about the current density, let us take J, that is NQ mu n into E. That is the value of current density. From this equation, this is not the complete equation, let me write it complete equation here. See, the inside the semiconductor, J is equals to what? N mu n, P mu P, Q times E. This is the complete equation, because I don't know that this is pure semiconductor, extrinsic, or this is intrinsic or extrinsic semiconductor. If it is intrinsic semiconductor, then it will follow this formula. If it is extrinsic semiconductor, if it is a p type semiconductor, then it will follow only that part, this part will be neglected. If it is an n type semiconductor, this part will be neglected, it will follow this one. So that is the main thing. See, basically at which part it is depending? It is depending on the applied electric field and carrier concentration. So what we can say, it will depend on both electric field and carrier concentration. So answer is C here, right? Next, An intrinsic semiconductor at absolute zero temperature. See, basically whenever you have an intrinsic, extrinsic, any type of semiconductor at 0 Kelvin, they always behave as a insulating material. So what will be the answer? They are behave like a insulator. I already discussed these things in detail in the classes, right? If you join the classes, you may check this thing how it will be done, right? I already discussed everything in detail. In an extrinsic semiconductor, the conductivity significantly depend upon what? See, if I am talking about the conductivity, the conductivity is sigma is equals to depend upon extrinsic semiconductor. Let's take it as an n-type semiconductor, nq mu n. This is the formula for the conductivity. See, inside this one, the major factor, that is n, the carrier concentration, right? So mu n is not that much affected because the value of carrier concentration is 10 raised to power 16 or 17, the order of 10 raised to power 16 or 17 per centimeter cube. That's why it is the most dominating factor here. So what we can see, majority charge carrier generated due to impurity doping. That will mostly affect the you can say the conductivity inside the extrinsic semiconductor, right? Minority carrier, because the value of the minority carrier is in the order of 10 raised to power 5 or 4, that will not affect that conductivity that much, right? So that's why we are neglecting the other part. If you see the formula for sigma is equals to n q mu n plus p q mu p, that is the exact formula. See, if you are taking a n-type semiconductor, then it is a majority carrier. Cp value of p is in the order of 10 raised to power 5, so this value is almost negligible as compared to this value. So that's why your conductivity will be decided only by the majority carrier concentration, right? Majority charge carrier is generated by due to thermal aggregation. See, if I talk about the thermal aggregation, I already discussed there will be equal amount of electrons and holes generated, so there will be no minority carriers. Minority charge carrier generated due to impurity dopings. I already discussed that thing. Due to minority carrier, it is not affecting that much. That is the main thing. Okay, so answer is A. See, basically what you are seeing, you have a pure silicon and you put that at room temperature, that is 298 or 300. Sometimes we take it 298, 25 degrees centigrade or 300, we are taking that thing. So basically at room temperature, right, at room temperature, if you take a pure silicon, so the conductivity of pure silicon is not that amount, right? It is very small quantity, you can say it is very small quantity. So what is happening, because we are currently using all the electronics devices at the room temperature, right? If you use the electronics devices at the room temperature, right, there is no doping and everything, you have a pure silicon, its conductivity is very low, because as you know, as you increase the temperature, charge carriers are generated, but that charge carrier is not that much sufficient that it can produce a sufficient amount of current to be flowed. So what is happening here, so at room temperature we can't use the electronics device at 400 Kelvin temperature, so that there will be a sufficient amount of electrons and holes generated, because we are using that electronics devices at room temperature and we want the conductivity should be sufficient amount that current will flow effectively from there, right? So what we can do, we will find other way to increase their conductivity. The other way is doping, right? If you understand that thing, there is other way. One way to increase the conductivity is temperature. When you increase the temperature at 300 Kelvin, but that conductivity is still very small. If you want the good conductivity, you need to increase the temperature further. But what is happening, you are using your electronics devices at your room temperature, so we can't use the temperature 350 or 400 Kelvin, because you are working at with your electronics, you can't work at 300 and 400 Kelvin. So what we have, we need to increase the conductivity further. We have to find the other way to increase the conductivity other than temperature. The other way what we found, that is called as doping. Doping is the other way increase the conductivity. Understood that thing? So basically we can use the doping to increase the conductivity. Drift velocity in the metal is, see, if you see the drift velocity, Vd is equals to what? Drift velocity is mu times E. Remember this formula. So what he is saying, inversely proportional to the force on the electron due to applied electric field. No, it is directly proportional to the mass of the electron. No, it is not depending on the mass of the electron. Proportional to the mobility of electron. Right? It is depend on the mobility of electron. That is the answer. At very high temperature, let us take n-type semiconductor. See, okay, let us discuss this concept. You have a n-type semiconductor. The conductivity of n-type semiconductor is 10 raised to power, let us take 10 raised to power 16, and there are holes are 10 raised to power 5. I'm just taking an example. It is not the correct value, right? There may be a different value. This is the number of holes inside a n-type semiconductor. There is a number of electrons inside n-type semiconductor. You are working at room temperature. Now you further increase the temperature. As you increase the temperature, the electrons and hole pair are generated. So what is happening? This P value will start increasing. That is at 10 raised to power 5. Now it is increasing. As you further increase the temperature, let us take at very high temperature, this P value is almost equals to this N value. So what we are seeing, you have a extrinsic semiconductor. Currently you have a extrinsic semiconductor, n-type semiconductor, but at very high temperature the sufficient amount of holes are generated, right? Let us take holes are generated 10 raised to power 16 and electrons also generated 10 raised to power 16, because when you increase the temperature, the electrons and hole pair are generated with equal amount. So what you are seeing, the electron will be added with these electrons, so it is become 2 into 10 raised to power 16. That is almost equals to 10 raised to power 16, which is hole concentration. So what you are seeing, as you increase the temperature, your n-type semiconductor will behave as a intrinsic semiconductor. Inside the intrinsic semiconductor, number of electrons and holes are equal. So what will be the answer? Answer will be B. The Fermi level in a p-type semiconductor lies closer to the, if you talk about the Fermi level, you can see from this figure, the Fermi level will lie nearer to valence band inside the p-type semiconductor. So what will be the answer? Answer will be top of the valence band, near to the top of the valence band. The resistivity of the metal is a function of temperature, because see, if I am talking about the resistivity of the metals, that is a function of temperature due to the vibrations of the atom. So what we can say, the lattice vibration increased with the temperature. That is the answer here. Okay, next. When donor atom are added inside the semiconductor, it is, so whenever you introduce the donor atom, see what is happening. Whenever we introduce the donor atom, there are electrons in the valence band currently without doping. So when you do the doping, they will jump to the conduction band, but they don't directly jump to the conduction band. First they will go to the another energy level. This energy level is called as discrete energy level, donor discrete energy level, right? So basically they are not directly jump to the conduction band. First they will go here, then they will go to the sufficient amount of energy to go to the conduction band. That is the phenomena. See, basically if you have it 0 degree Kelvin, if you do the doping, the electrons will jump to this level here, only this donor energy level. They don't directly jump to the conduction band. They jump to this donor energy level, right? That's why at 0 Kelvin they are not getting the sufficient amount of energy so that they can jump to the conduction band. At 0 Kelvin this n-type semiconductor will work like a insulator, right, not a conductor. So that is the main reason. See what is happening, so they will jump to the another energy level, that is called as donor energy level. So when the donor atom are added in the It increase the band gap will not be decrease the band gap, it is not. Introduce a new narrow band gap near the conduction band, that is discrete, right? And introduce a new discrete energy level below the conduction band, that will be the answer, right? It is introducing a new discrete energy level, this is called discrete donor energy level, right? So that will be the answer here. An intrinsic semiconductor having Ni is given to you and doped with the his assume all the donor atom is ionized, right? Whole concentration we have to find. Ni is given to you 10 raised to power 16 meter cube per meter cube, and N is given to you 10 raised to power 22, because donor atom make the semiconductor as a n-type semiconductor. So what we can found, we have to find the whole concentration P. So what we can do, we can use the mass action law and we will find the value, that is going to be how much, 10 raised to power 10. That's the answer. The mobility of electron in the semiconductor is defined as mobility of electron is Vd upon E. It is the ratio of drift velocity over electric field. So we can say diffusion velocity, no, drift velocity per unit electric field. So answer will be D. Number of electrons hole pair generated per incident of you can say the photon is called as quantum efficiency. The answer will be quantum efficiency. The method of rising a particle from lower energy state to higher energy state is called as what? That is called as population inversion, right? When you are taking an electron from lower energy station to higher energy state, that is called as population inversion. Okay, the electrical conductivity of a semiconductor increased when a radiation of wavelength shorter than this is incident, right? So band gap of the semiconductor, see, you remember this, Eg is equals to what? 1.24 divided by lambda. Lambda should be in micrometer, and the energy we will quote, that is in electron volt. So energy is going to be 1.24 divided by 1000 nano. Convert that 1000 nano, that will be 1000 nanometer is equals to 1 micrometer. So it is going to be 1.24 electron volt. So energy is going to be what? 1.24, yeah, 1.2 electron volt. The exact value is 1.24 electron volt. In a semiconductor, hole are exist in which band? The holes are existing in valence band, right? Electrons are existing in conduction band. Drift current inside the semiconductor depends on what? See, drift current, I already discussed this thing in the starting, that the drift current is depending on both electric field and carrier concentration, right? Next question. In a junction, built-in potential depend on what? See, if you talk about inside the junction, PN junction, the built-in potential formula is VBI is equals to KT over Q ln Na ND over Ni square. So it is depend on doping density and as well as the temperature. It will depend on both the things, right? So answer will be C here. The electron rising through a potential of 500 volt acquire energy. See, whenever you are calculating the energy, see, 1 electron volt is equals to what? When it will be excited by 1 volt. So if you excite one electron by 1 volt, then it will be acquiring a energy of 1 electron volt. So if you are rising an electron by a potential of 500, then it will be acquiring energy of 500 electron volt. So if you remember the definition of 1 electron volt is the energy acquired by the electron when it will be excited from the 1 volt. So if I excited that electron by 500 volt, then it will be gain the energy of 500 electron volt. That will be the answer. N-type pure semiconductor is N-type semiconductor is positively charged, negatively charged, electrical neutral, and none of this. See, every time if he is asking for the any type of semiconductor or any type of devices, if you are not providing any charge from anywhere, then it is always electrical neutral. So either it is n type, p type. See, basically we are introducing the n impurity atom. See, whenever one electron out there, then the atom will go gain a, see, one electron is removed, electron will have negative charge, the atom will gain the positive charge, but still the complete semiconductor is electrical neutral, right? Either the current will flow through the any wire or anywhere, that is also electrical neutral. The electron enters from one end, the same amount of electron will leave from the other end, still it is it is electrical neutral. If you are rubbing that surface, you are extracting the electron from there, then it will become either positive charge or negatively charged. But if you do not doing that much, you are not extracting the electrons and holes, then it is remain electrically neutral. So what will be the answer? Answer will be C. So these are the some questions, right? If you want more detail about this, you can join our module in which I already discussed all the things in detail. EDC is currently going on, right? And I already discussed in these all these concepts in detail there, so you may join that program. Hopefully this will help you in your preparation. Thank you.